Hello, welcome to part 2 of lesson 5, where we will continue our discussion of routers. This is another lesson from my new course on networking fundamentals, which will teach you everything you need to understand how data flows through the internet. In this lesson, we'll continue right where we left off from the last video. In part 1 of this lesson, we used this topology to illustrate that routers have an IP address and a MAC address in each network that they are connected to. We also learned that routers maintain routing tables, which is a map of every network that each router knows about, and that routes in that routing table can be populated in one of these three ways. We showed you all this by showing you Router 1 and Router 2's routing tables, and showed you how each router populates its routing table using one of these three methods. Now all of this was covered in great detail in part 1 of this video. If you haven't seen that video yet, go ahead and pause this video and watch that one first, as this video is simply going to build upon these concepts. Now, something we didn't mention in part 1 of this video is that not only do routers have routing tables, but routers also have ARP tables. ARP, if you recall, is a mapping of a layer 3 address like an IP address to a layer 2 address like a MAC address. Now we discussed ARP in lesson 3 of this series. In that lesson, I told you that everything with an IP address has an ARP table. Well, just like we just mentioned, routers also have IP addresses. Therefore, they also have ARP tables. And in each case, the router's ARP tables are going to maintain a mapping of IP addresses to MAC addresses of all the nodes in directly connected networks. Take a look at R1's ARP table right here. Notice in the 1044 network there is only one other node other than the router. And router 1 is going to have an ARP entry correlating to the IP address and MAC of host A. For this network, there are two other nodes in that network other than router 1. And router 1 is going to have an ARP entry for each of them, this one belonging to host B, and this one belonging to router 2. And router 2 is the same way. There's only one other node in this network, that's host C, and there's the ARP mapping for host C. And then in this network over here, there are two other nodes other than R2, and you have a mapping for each of them in router 2's ARP table. Now the thing about ARP tables is that unlike routing tables, ARP tables actually start out empty. They will get populated dynamically as needed as traffic is flowing through this network. That's different from the routing table. The routing table has to be populated ahead of time. Recall that if a router receives a packet that it doesn't know how to deliver, the router is just going to drop that packet. But with ARP, if the router doesn't have an ARP entry it needs, it can simply do the address resolution process to figure out what it needs. We're going to show you how router 1 and router 2 use their routing tables and ARP tables in order to get a packet all the way from host A through both of these routers to host C. It's going to start with host A having some data it needs to send to host C. Host A knows the IP address it's trying to speak to, so it's able to construct a layer 3 header that's going to include a source IP address of host A and a destination IP address of host C. Now we discussed some reasons of why host A might already know the IP address it's trying to speak to. We reviewed that back in lesson 3. Feel free to check that out if you want a refresher. Either way, host A can look at the destination IP address and compare that to its own IP address to determine that what it's trying to speak to is on a foreign network, which means this packet must be sent to host A's default gateway, which in this case is R1. The issue is if this is the first packet that host A has sent, host A doesn't know router 1's MAC address and therefore cannot construct the necessary layer 2 header, which would take this packet from host A's NIC to router 1's NIC. So, before host A can send the packet, host A is going to have to perform ARP. So host A is going to send an ARP request for the IP address of R1, 10.044.1. That ARP request is going to ask for the MAC address for whoever owns the IP 10.044.1. Notice in the ARP request, host A is going to include its own IP to MAC address mapping. This ARP request will be sent across the wire, where it will be received by router 1, and when router 1 receives the ARP request, router 1 will be able to learn the ARP mapping of the sender of the ARP request. Recall that the sender included the ARP mapping of host A, and there's nothing preventing router 1 from simply adding that ARP entry to its ARP table upon receiving the ARP request. Now router 1 needs to generate a response. That response will include the ARP mapping that host A was trying to resolve. When that ARP response gets back to host A, host A will populate its ARP entry with the MAC address of its default gateway. And now, host A has everything it needs to properly construct the layer 2 header, which will get this packet from host A to the router. Host A can now send all of this to the router. When the router receives this packet, the first thing the router is going to do is discard the layer 2 header. Remember, that header only existed to take that packet from this MAC address to this MAC address. It did so successfully, so we can discard that layer 2 header. Now router 1 will look at the destination IP address in its routing table. It's going to try and find a match to determine where to send this packet next. It'll see that there's a match right here, which will tell router 1 that the next hop for this particular packet is the IP address 10.0.552, which is router 2's IP address. Now, router 1 needs to construct a layer 2 header, which will take this packet from this MAC address to this MAC address. The problem is at this point, router 1 does not have an ARP entry for the IP address 10.0.55.2. Therefore, router 1 cannot construct the layer 2 header as necessary, which means router 1 is going to have to perform the address resolution protocol. Router 1 will send an ARP request for the IP address 10.0.55.2. Just like before, the ARP request includes the sender's ARP mapping. This is going to allow R2 to learn the ARP mapping of the sender of that ARP request. Upon receiving the ARP request, R2 will learn that something with the IP address 10.0.55.1 has the MAC address EEE3. Now, R2 will generate an ARP response. This ARP response is the ARP mapping that router 1 was trying to discover. When router 1 receives this ARP response, router 1 will be able to complete its ARP entry, and therefore able to create a layer 2 header, which will get the packet through to the next hop. Now, this packet can be sent from this NIC to this NIC. Once it gets there, router 2 is going to receive the packet and discard the layer 2 header. Again, that header only existed to go from here to here. Then, router 2 will look at the destination IP address in the routing table to try and determine what to do with that packet next. It'll find a match right here, indicating that this packet needs to be delivered out the left interface. Since router 2 is now delivering this packet through a directly connected route, it knows that this is actually the final hop for this particular packet, because the destination exists in a directly connected network. So router 2 will need to construct a layer 2 header, which will take this packet from router 2's NIC to host C's NIC. But just like before, router 2 currently does not know host C's MAC address, and therefore cannot create the layer 2 header. Router 2 is going to have to send an ARP request to resolve the layer 2 address for host C. This will follow the same process we've already outlined. Host C will learn the MAC address mapping for router 2 by receiving the ARP request from router 2. This will be useful for the return traffic back to host A. Then host C will generate an ARP response. This ARP response is going to include the ARP mapping that router 2 was trying to resolve. Once router 2 receives the ARP response, it'll populate its ARP table with the appropriate MAC address, and then it can finally create the appropriate layer 2 header to get the packet to host C. When host C receives this packet, it's going to discard the layer 2 header. Again, this header's purpose was simply to take the packet from this NIC to that NIC. Then host C is going to discard the layer 3 header. The purpose of that header was simply to take the data from this IP address to this IP address, and finally host C will process the data. And that is every single step that needs to happen in order to get data from host A to host C. Next, I'm going to show you what needs to happen in order to get a response from host C back to host A. But you'll notice the way back will go much quicker because all of the necessary ARP entries have already been populated. Just like before, it's going to start with host C having some data to go to host A. Now these routers aren't going to know that this is actually response data. From the perspective of these routers, this is just a bunch of ones and zeros. Host C knows this data needs to get to host A, so it'll create a layer 3 header with a source IP address of host C's IP address and a destination IP address of host A's IP address. And since host C knows that the destination IP address is on a foreign network, host C knows that this packet needs to go to its default gateway, which in this case is router 2. And since host C already has the ARP mapping for router 2, it can create the layer 2 header necessary to get this packet from this NIC to this NIC. Remember that host C learned the MAC address of router 2 when router 2 asked for host C's ARP entry. Either way, that's what's going to occur to get this packet sent to R2. Once R2 receives the packet, it'll discard the layer 2 header, then look up the destination IP address in its routing table to determine what to do with this packet next. It'll find a match for this IP address with this route right here, which is going to tell router 2 that the next hop of this particular packet is the IP address 10.055.1, which is router 1's IP address. And since router 2 already has an ARP mapping for router 1, router 2 can instantly create the necessary layer 2 header to get the packet across this hop. So with that layer 2 header created, router 2 can now send the packet to router 1. Once it arrives to router 1, again, router 1 will discard the layer 2 header and then look up the destination IP address in its routing table. It'll find a match for this route right here, which tells router 1 that this particular packet needs to be delivered out the right interface to its final hop. And since router 1 has the ARP mapping for the IP address 10.044.9, router 1 is able to construct a layer 2 header which will get the packet across to its final hop. This will then allow router 1 to send this packet to host A. Once host A receives the packet, host A will discard the layer 2 header, then host A will discard the layer 3 header, and finally host A will process the response data. And that is everything that occurs to get the response data from host C all the way back to host A. And that wraps up the major ideas I wanted to communicate to you in this lesson. The main takeaways are understanding how the routers are going to use their routing tables and their ARP tables in order to forward packets across a network. But before I let you go, there's still one last thought I want to leave you with. Everything we did between router 2 and router 1 in order to move data from host C to host A would repeat for any amount of routers in the path. In each case, every router in the path would look up the destination IP address in their routing table to determine the next hop IP address, and then construct a layer 2 header with the appropriate MAC addresses to get the packet across to the next hop. If for whatever reason a router doesn't know the destination MAC address, that router will perform ARP as necessary. These steps are the same steps we just illustrated to get a packet from router 2 to router 1. But those same steps would also occur if there were many other routers in the path between router 2 and router 1. What we just illustrated essentially showed you how a packet gets from host C all the way through to host A, whether host A is on the other side of 2 routers, or 5 routers, or the other side of the internet. In fact, the internet is really nothing more than just a series of routers that are handing packets off between other routers. And with that, we finally wrap up our discussion on routers. The main takeaway is understanding the process that every router will follow and how the routers will use their routing table and their ARP tables to move packets along. I hope you enjoyed this video. I want to thank you for watching, and we'll see you in the next one. Hey YouTube, I hope you enjoyed that free lesson. I'm releasing this content for free to see how much interest there would be in a full Networking Fundamentals course taught in the same practical networking style. If you want the full course to be created, you have to help me out by spreading the word about this free module. If this content gets enough attention, I will definitely create the full course based upon your suggestions for what you want in a Networking Fundamentals course. Besides, I'm sure you know someone that would also benefit from learning how data flows through the internet, so you'd be helping them by sharing these videos. You could also further help me out with the YouTube algorithm by liking, subscribing, and leaving a comment below. I would appreciate it greatly, and I read and respond to every comment. Otherwise, feel free to join fellow learners and fans of practical networking on Discord. The invite is available at pragnet.net/discord. Thank you for watching, and we'll see you in the next video.